we'll continue. Normally today we can finish all the new things in this chapter, and from next week we'll begin to revise. Not yet, but normally today we can finish all the whole chapter 9, and that will be the end of this semester. And next week we'll begin to do some revision. We'll, as usual, we'll see some. We'll do some revision about previous class, about what we had in previous classes. For example, the three different types of software maintenance. Do you remember the three different types of software maintenance? Add or modify the system's functionality. Okay, we may have different name for them. As you said, we may have fault repairs. We can have the adaptation, environmental adaptation. We can have also the functionality addition. And for the fault repairs, we have talked about three kinds of errors. Thank you very much, Kaya, Roy, and Sajid. And three types of errors for fault repairs. Three types of errors for fault repairs. Not exactly. In the last week, not last week. I think it was yesterday. We have talked about those three types of errors, and we have talked about which one is the cheapest, which one is the most expensive, as well as the three types of software maintenance. Do you remember? For the fault repairs, we may have the coding errors, which are usually relatively cheap to correct. Coding errors. And then we have and the other two errors, Roy has mentioned them. The second one is the design errors, which are more expensive than coding errors, as design errors may involve rewriting several program components. And the third type is the requirement errors. They are the most expensive to repair because of the extensive system redesign which may be necessary. So we have these three types of errors: coding errors, design errors, and requirement errors. These three types of errors for fault repairs. Later, we have talked about the 4 reasons for which it is usually more expensive to add functionality after a system is in operation than it is to implement the same functionality during development. Not term is team. Like said, Kaya. Team. Yeah, 4 reasons for which it is usually more expensive to add functionality after a system is in operation than it is to implement the same functionality during development. Yeah, the first one is the team stability, and the second one, yeah, here is the first reason. Thank you, Kaya. And contractual responsibility. Yeah, we can say that. But what is in our PDF, I think it's not the same thing. Maintenance corrupts the software structure. Okay. This part is here. I think it should be somewhere. Yeah, here. We have these four reasons or 4 factors. Team stability. Maintenance costs are reduced if the same staff are involved with them for some time. As we said, after a system has been delivered, okay, yeah. Kaya, I'm sorry for the second one. Contractual responsibility is the same, but not for the fourth one, the third one and the fourth one. Yeah, aging software is nearly the same. It could, yeah. But yeah, staff skills is quite different. For the team stability, usually after a system has been delivered, it is normal for the development team to be broken up and for people to work on new projects. And the new team or the individuals responsible for system maintenance do not understand the system or the background to system design decisions. So they need to spend time understanding the existing system before implementing changes to it. And the second one is the contractual responsibility. It's like the poor development practice. The contract to maintain a system is usually separate from the system development contract, and the maintenance contract may be given to a different company rather than the original system developer. And this factor, along with the lack of team stability, means that there is no incentive for a development team to write maintainable software. If a development team can cut corners to save effort during development, it is worthwhile for them to do so, even if this means that the software is more difficult to change in the future. And the third one, yes, third factor is the staff skills. Maintenance staff are often relatively inexperienced and unfamiliar with the application domain. So maintenance has a poor image among software engineers. It is seen as a less skilled process than system development, and is often allocated to the most junior staff. We have the factors of staff skills also. And the fourth reason is the program age and structure. As program age, their structure is degraded, and they become harder to understand and change. Okay, thank you, Kaya. Yeah. And yeah, we have also talked about 3 factors to evaluate the relationships between our system and its environment. And some systems have a very complex relationships with their external environment, and changes to that environment inevitably result in changes to the system. And we should assess 3 factors to evaluate the relationships between a system and its environment. Which are the 3 factors to evaluate the relationships between a system and its environment? Predicting maintainability. Yeah, number of and complexity of system interfaces. Yeah, like say back. Yeah, Roy has listed the first one. Yeah, and Kaya has listed the third one. Now of inherent volatile requirements. Yeah. Okay. Yeah. It's number of inherent volatile requirements. And yeah, thank you, Roy and Kaya. You have completed the 3 factors. Yeah, the first one is the number and the complexity of system interfaces. The larger the number of interfaces and the more complex these interfaces, the more likely it is that interface changes will be required as new requirements are proposed. And the second one is the number of inherent volatile system requirements. Requirements that reflect organizational policies and procedures are likely to be more volatile than requirements that are based on stable domain characteristics. And the third one is the business processes in which the system is used. As business processes evolve, they generate system change requests. And the more business processes that use a system, the more the demands for system change. Yeah, what a good teamwork. You have done a good job. Thank you very much, Kaya and Roy. So now we'll continue with what we were, where we were yesterday here. Yeah, in this part, we have said that there are 5 activities in this reengineering process. These 5 activities are source code translation, reverse and reengineering, program structure improvement, program modularization, and data reengineering. We'll see these 5 activities in detail. The first one is the source code translation. We use a translation tool to convert the program or the code from a programming language to a more modern version of the same language or different language or new language. And for the reverse engineering, we analyze the program. We extract information from it in order to understand it better, and this helps to document its organization and functionality. Now, this process is usually completely automated. Then the third activity is the program structure improvement. This activity concerns restructuring automatically for understandability. The control structure of the program is analyzed and modified to make it easier to read and understand. And this can be partially automated, but some manual intervention is usually required. Then the fourth activity is the program modularization. Here, related parts of the program are grouped together, and where appropriately, redundancy is removed. In some cases, this stage may involve architectural refactoring, a system that uses different data stores may be refactored to use a single repository, and this is a manual process. The fifth one, data reengineering. In this activity, the data processed by a program is changed to reflect program changes. And this may mean redefining database schemas and converting existing databases to the new structure. We should usually also clean up their data, and this activity involves finding and correcting mistakes, removing duplicate records, etc. Tools are available to support data reengineering. So you see, program reengineering may not necessarily require all of these activities. I'm sorry. If we still use the application's programming language, we may don't need this activity, source code translation. And in another situation, if we can do all re-engineering automatically, then recovering documentations through reverse engineering may be unnecessary. And data re-engineering, it is only required if the data structures in the program change during system re-engineering. So you see, we may just need some of these activities for program re-engineering, and to make the re-engineered system interoperate with the new software, we may have to develop adapter services. This will have the original interfaces of the software system and present new data structures interfaces that can be used by other components. And this process of legacy system wrapping is an important technique for wrapping large-scale reusable services. Yeah, we'll talk about the legacy system in detail. And this figure is a spectrum of possible approaches to re-engineering. Yeah, we see that the core of re-engineering depend on the extent of the work that is carried out. Costs increase from left to right, so that source code translation is the cheapest option, and re-engineering as a part of architectural migration, it is the most expensive. For the factors for re-engineering cost, we may have these ones. The first one is the quality of the software to be re-engineered. The second one, I'm sorry, why it doesn't work very well. Yeah, okay. The quality of the software to be re-engineered, the tool support available for re-engineering. We have the extent of the data conversion, which is required, the availability of expert staff for engineering. This can be a problem with old systems based on technology that is no longer widely used. You see, these are factors that may affect the reengineering cost. And the problem with software reengineering is that there are practical limits to how much we can improve our system by reengineering. And it isn't possible, for example, to convert a system written using a functional approach to an object-oriented system. And major architectural changes may not be carried out automatically, so they are very expensive. Although re-engineering can improve maintainability, the re-engineered system will probably not be as maintainable as a new system developed using modern software re-engineering methods. The preventative maintenance by refactoring. Refactoring is the process of making improvements to a program to slow down degradation through change. Here, we can think of refactoring as preventative maintenance that reduces the problem of future change. Why? As we know, for the refactoring, it means modifying a program to improve its structure, to reduce its complexity, or to make it easier to understand. And refactoring is sometimes considered to be limited to object-oriented development, but the principles of refactoring can be applied to any development approach. And when we refactor a program, we should not add functionality, but we should rather concentrate on program improvement. Before we have talked about re-engineering, and now we talk about the refactoring. Although re-engineering and refactoring, they are both intended to make software easier to understand and change. They are not exactly the same thing. Re-engineering takes place after a system has been maintained for some time and maintenance costs are increasing. We use automated tools to process and re-engineer a legacy system to create a new system that is more maintainable. However, refactoring, it is a continuous process of improvement throughout the development and evolution process, and it is intended to avoid the structure and code degradation that increases the costs and difficulties of maintaining our system. So you see, the difference is quite big between these two activities. For re-engineering, it occurs usually after a system has been maintained for some time. And for refactoring, it's a continuous process throughout the development evolution. Also, the objective of each activity is different. For re-engineering, we want to create a new system that is more maintainable. And for refactoring, we want to avoid the structure and code degradation. So we keep the same system. And in fact, refactoring is an inherent part of agile methods. As we have talked about extreme programming, we know that these methods are based around change, and program quality is therefore liable to degrade quickly. So agile developers frequently refactor their programs to avoid this degradation. And the emphasis on regression testing in agile methods lowers the risk of introducing new errors through refactoring. And any errors that are introduced should be detectable as previous successful tests should then fail. However, refactoring is not dependent on other agile activities and can be used with any approach to development. Yeah, we have some stereotypical situations. We may call them bad smells, in which the code of a program can be improved. Here we have some examples of bad smells that can be improved through refactoring. The first one is the duplicate code. The same or very similar code may be included at different places in a program, and this can be removed and implemented as a single method or function that is called as required. The second type is the long methods. If a method is too long, it should be redesigned as a number of shorter methods. The third one is the switch case statements. These often involve duplication, where the switch depends on the type of a value. The switch statements can be scattered around a program, and in object-oriented programming language, we can often use polymorphism to achieve the same thing. In this way, we can make the program simpler and easier to understand. The fourth type is the data clumping. Data clumps occur when the same group of data items or fields, classes, parameters, and methods reoccur in several places in a program. This can often be replaced with an object that encapsulates all of the data. It is also in object-oriented programming language, we may solve it efficiently. And the fifth example is the speculative generality. This occurs when developers include generality in a program in case it is required in the future, and this can often simply be for these we call them bad smells. We may change or improve the quality as proposed in each example, and most of them, as we have said, may be solved by some program by the notion or the idea of object-oriented idea. This is the part of software maintenance. And later we'll talk about the legacy system management. I think I'll make a break here. If you want, you can have a break of 10 minutes and I will note for your attendance. We'll continue. We are at the last section, the legacy system management. For the moment, do you have some questions about what is before? Don't hesitate to precise your question here. Yeah, I mean, we are back. If you don't have any question, we'll continue with the last section, the legacy system management. No. We have still next week. And next week we'll have some revision. We have still 3 lectures for the revision. Yeah. Then we'll wait for the notice of exam, perhaps. Okay. So for the legacy system management, okay, there are so many things. Most organizations usually have a portfolio of legacy systems that they use with a limited budget for maintaining and operating these systems. They have to decide how to get the best return on their investment. And this includes making a realistic assessment of their legacy systems and then deciding on the most appropriate strategy for evolving these systems. So you see, organizations that rely on legacy systems must choose a strategy for evolving these systems. And here we have listed 4 strategies. Let's see these 4 strategic options in detail. The first one is to scrap the system completely and modify business processes so that it is no longer required. This option should be chosen when the system is not making an effective contribution to business processes. And this option is commonly occurs when business processes have changed since the system was installed and are no longer reliant on the legacy system. In this way, we can scrap or abandon the system completely. The second option is that leave the system unchanged and continue with regular maintenance. This option should be chosen when the system is still required but is fairly stable and the system users make relative few change requests. In this way, we can leave the system unchanged and continue with regular maintenance of the system. And the third option is transform the system by re-engineering to improve its maintainability. So we re-engineer the system to improve its maintainability. This option should be chosen when the system quality has been degraded by change and where a new change to the system is still being proposed. This process may include developing new interface components so that the original system can work with other newer systems. And the last option is to replace the system with a new system. Here, we may replace all or part of the system with a new system. This option should be chosen when factors such as new hardware mean that the old system cannot continue in operation, or where off-the-shelf systems would allow the new system to be developed at a reasonable cost. In many cases, an evolutionary replacement strategy can be adopted in which major system components are replaced by off-the-shelf systems with other components reused wherever possible. So you see, these 4 strategies, they have different appropriate situations. So when we have some legacy systems to be managed, we need to choose the strategic option according to different situations. Yeah, we say that the strategy chosen should depend on the system quality and its business value. Yeah. In fact, these options, they are not exclusive. And when our system is composed of several programs, different options may be applied to each program. And when we are assessing our legacy system, we have to look at it from a business perspective, as we say, its business value, and a technical perspective, the system quality. From a business perspective, we have to decide whether or not the business really needs the system. And from a technical perspective, we have to assess the quality of the application software and the system's support software and hardware. We then use a combination of the business value and the system quality to inform our decision on what to do with the legacy system. Yeah. For example, here we assume that an organization has 10 legacy systems. You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 legacy systems. And we should assess the quality and the system quality and the business value of each of these systems. We may then create a chart like this showing relative business value and system quality. As you can see from this figure, we see that there are 4 clusters, 1, 2, 3, 4, 4 clusters of systems. The first one is low quality and low business value. These kind of systems, keeping these systems in operation will be very expensive, and the rate of the return to the business will be fairly small. So these kind of systems should be scrapped. We can scrap them completely. And for the second second type, we may say this one. We have the low quality, high business values. These systems are making an important business contribution, so they cannot be scrapped. However, their low quality means that it is expensive to maintain them. So these systems should be re-engineered to improve their quality. They may be replaced if a suitable off-the-shelf system is available. And the third type is the high quality, low business value, this part. These are systems that don't contribute much to the business, but which may not be very expensive to maintain. It is not worth replacing these systems, so no more system maintenance may be continued if expensive changes are not required and the system hardware remains in use. If expensive changes become necessary, the software should be scrapped, as it may come here as low business value and low quality. For the moment, it has a high system quality, so we can continue to maintain it. And the fourth type is this one, high quality, high business value. These systems have to be kept in operation. However, their high quality means that we don't have to invest in transformation or system replacement. So we just continue the normal system maintenance. Yeah, here we have these four categories: low quality, low business value. These systems should be scrapped. Low quality, high business value. These make an important business contribution but are expensive to maintain. So we should re-engineer or replace the system if a suitable system is available. For the high quality, low business value, we can replace it with quartz, scrap completely, or maintain. It depends on different situations. And if we have a high quality, high business value legacy system, we should continue in operation using normal system maintenance. Okay. So when we, how can we assess business value? Assessment should take different viewpoints into account. We need to take into account the opinions of system end users, business customers, line managers, IT managers, senior managers. To assess the business value of a system, we have to identify system stakeholders as these end users of the system, their managers, etc. And we have to ask a series of questions about the system. In fact, interviews, we need to interview different stakeholders and collate results. There are four basic issues that we have to discuss for assessing business value. The first one is the use of the system. If systems are only used occasionally or by a small number of people, they may have a low business value. A legacy system may have been developed to meet a business need that has either changed or that can now be made more effectively in other ways. So we have to be careful, however, about occasional but important use of systems. For example, in a university, a student registration system may only be used at the beginning of each academic year. However, it is an essential system with a high business value. So you see, there are some systems that we may just use it once a year, twice a year, but it may have a high business value, not just like they hear what we said. If we use less, then the business value is lower. And we have still some special cases to which we need to pay attention. The second basic issue is that the business processes that are supported. A system may have a low business value if it forces the use of inefficient business processes. When a system is introduced, business processes are designed to exploit the system's capabilities. If the system is inflexible, changing these business processes may be impossible. So, however, as the environment changes, the original business processes may become obsolete. Therefore, a B system may have a low business value because it forces the use of inefficient business processes. The third issue is the system dependability. If a system is not dependable and the problems directly affect business customers, the system has a low business value. System dependability is not only a technical problem but also a business problem. I said here, if a system is not dependable and the problems directly affect the business customers, or mean that people in the business are diverted from other tasks to solve these problems, then that means this system has a low business value, as it is we can consider it as an alternative. It's not necessary. Then the fourth issue is the system outputs. If the business depends on system inputs, then the system has a high business value. The key issue here for the system outputs. The key issue is the importance of the system outputs to the successful functioning of the business. If the business depends on these outputs, then the system has a high business value. Conversely, if these outputs can be easily generated in some other way, or if the system produces outputs that are rarely used, then its business value may be low. So you see, we have different basic issues to discuss when we assess the business value of our system. You see here for business process assessment, we may ask some questions. How well does the business process support the current goals of the business? For the environment assessment, we may ask how effective is the system's environment and how expensive is it to maintain? For the application assessment, we may ask what is the quality of the application software system? For example, let's assume a company provides a travel ordering system that is used by staff responsible for arranging travel. For this company, they can place orders with our travel agent. Tickets are then delivered and the company is invoiced for these. However, a business value assessment may reveal that this system is only used for a fairly small percentage of travel orders placed. People making travel arrangements find it cheaper and more convenient to deal directly with travel suppliers through their website, and this system may still be used, but there is no real point in keeping it. The same functionality is available from external systems. So you see, In another way, we can say that a company has developed a system that keeps track of all previous customer orders and automatically generates reminders for customers to reorder goods. And this results in a large number of repeat orders and keeps customers satisfied because they feel that their supplier is aware of their needs, and the outputs from such a system are very important to the business, and the system therefore has a high business value. We can use a viewpoint-oriented approach and seek answers from stakeholders. We may ask these questions. Is there a defined process model and is it followed? Do different parts of the organization use different processes for the same function? How has the process been adapted? What are the relationships with other business processes and are these necessary? Is the process effectively supported by the legacy application software? As we have taken our travel ordering system as an example, we say that this system may have a low business value because of the widespread use of web-based ordering. Customers may order it from external systems easily. And here, this figure shows the factors that we should consider during the environment assessment. You see, we should notice that these are not all technical characteristics of the environment. We also have to consider the reliability of the suppliers of the hardware and support software. If these suppliers are no longer in business, there may not be support for their systems. As we have talked before, for different factors, we may ask different questions. For example, for the supplier stability, we may ask if is the supplier still in existence? Is the supplier financially stable and likely to continue in existence? If the supplier is no longer in business, does someone else maintain the systems? For the failure rate, does the hardware have a high rate of reported failures? Does the support software crash and force system restarts? For the age, we may ask how old is the hardware and software. The older the hardware and software and support software, the more obsolete it will be. It may still function correctly, but there could be significant economic and business benefits to moving into a more modern system. For the performance, we may ask the question, is the performance of the system adequate? Do performance problems have a significant effect on system users? We may also have other factors like support requirements. For the question, what local support is required by the hardware and software? If there are high costs associated with this support, it may be worth considering system replacement. For the environment assessment, you see, as we have said, there are not all technical characteristics of the environment. We have also we have to also consider the reliability of the supplier of the hardware and software and support software. For the maintenance costs, we may ask what are the costs of hardware maintenance and support software licenses. Older hardware may have higher maintenance costs than modern systems, and support software may have high annual licensing costs. For the interoperability, we may ask, are there problems interfacing the system to other systems? Can compilers, for example, be used with current versions of the operating system? Is hardware emulation required? So you see, if the suppliers of the hardware and support softwares are no longer in business, there may not be support for their systems. So we need to consider these factors to assess the environment. And when we assess the technical quality of an application system, we have to assess another range of factors that are primarily related to the system dependability, the difficulties of maintaining the system, and the system documentation. We may also collect data that will help us judge the quality of the system. You see, for the understandability, we may ask the questions, how difficult is it to understand the source code of the current system? How complex are the control structures that are used? Do variables have meaningful names that reflect their function? You see, with these questions, we may have a general idea about the complexity to understand our system. And the second factor to use here is the documentation. What system documentation is available? Is the documentation complete, consistent, and current? You see, with the documentation, with specified or detailed documentation, we may understand the system more easily. The third factor is the data. Is there an explicit data model for the system? To what extent is data duplicated across files? Is the data used by the system up to date and consistent? For the performance, we may ask the question, is the performance of the application adequate? Do performance problems have a significant effect on system users? And for the programming language, we may ask, are modern compilers available for the programming language used to develop the system? Is the programming language still used for new system development? As we said, if these questions are no, then we need a translation, a tool. For the configuration management, we may ask the questions like, are all versions of all parts of the system managed by a configuration management system? Is there an explicit description of the versions of components that are used in the current system? And for the test data, we may ask the questions like, does the test data for the system exist? Is there a record of regression tests carried out when new features have been added to the system? You see, before we have said that regression tests are important to guarantee the feasibility or reliability of the system. Also, we have the factor like personnel skills. We may ask the questions, are there people available who have the skills to maintain the application? Are there people available who have experience with the system? These, you see, these questions can show the maintainability and availability of the system by personnel skills. Here we have talked about some, you see, documentation, data, test data, etc. Data that may be useful in quality assessment are these data. So we may collect quantitative data to make an assessment of the quality of the application system. These data include the number of system change requests, the number of different user interfaces used by the system, and the volume of data used by the system. For the number of system change requests, system changes usually corrupt the system structure and make further changes more difficult. So the higher this accumulated value, the lower the quality of the system. So it's better that the number of system change requests is small. And for the number of user interfaces, different user interfaces used by the system, this one, it is an important factor in forms-based systems, where each form can be considered as a separate user interface. And the more interfaces, the more likely that there will be inconsistencies and redundancies in these interfaces. Yeah, as what we have said before, if our system has different stakeholders, different users, they may have different requirements, and among these requirements, there may be some inconsistencies. And for the third one is the volume of data used by the system. The higher the volume of data, that means the number of files, the size of databases, etc. And the more likely that it is that there will be data inconsistencies that reduce the system quality. So, if we want to judge the quality of the system, we may consider these different data. Ideally, objective assessment should be used to inform decisions about what to do with our legacy system. However, in many cases, decisions are not really objective, but are based on organizational or political considerations. For example, if two businesses emerge, the most politically powerful partner will usually keep its systems and scrap the other systems. If senior systems management in an organization decide to move to a new hardware platform, then this may require applications to be replaced. If there is no budget available for system transformation in a particular year, then system maintenance may be continued, even though this will result in higher long-term costs. Yeah, so you see, it's not so easy to manage legacy systems. We have so many things to assess, and we have so many different situations to manage. Now, yeah, we have gone through all points in this chapter. Oh, yeah, we have, now we will see the key points in this chapter. Yeah, for some people or some developers or people from other domains, they may think software development and software evolution are different things. may in fact software development and evolution can be thought of as an integrated, iterative process that can be represented using a spiral model. Yeah, we have shown this model in the first section of this chapter. For custom systems, the costs of software maintenance usually exceed the software development costs. Yeah, we have said that the cost of software maintenance may take up 2/3 of the whole course. So it's normal that the cost of software maintenance exceed the software development costs. We should not ignore or downestimate the cost of software maintenance. We should pay attention to its importance. And the process of software evolution is driven by requests for changes and includes change impact analysis, release planning, and change implementation. Yeah, if there are no requests for changes, we may don't consider the process of software evolution. And when we begin this process, we may have different activities, as we say here, change impact analysis, release planning, and change implementation. According to Lemann's laws, we have extracted or we have explained these laws in detail. According to these laws, such as the notion that change is continuous, we describe a number of insights derived from long-term studies of system evolution. Yeah, we have talked about 3 types of software maintenance. Yeah, we may have different name for them. Here we may call them bug fixing, like faults, modifying software to work in our new environment. We have said adapting to new environment, and implementing new or changed requirements. Yeah, perhaps we have said the addition or new functionalities. Here we say that software reengineering is concerned with restructuring and redocumenting software to make it easier to understand and change. It is the objective of software reengineering. On the other hand, the refactoring, which is a form of preventative maintenance, the objective is to make program changes that preserve functionality. And we should assess the business value of our legacy and the quality of the application to help decide if our system should be replaced, transformed, or maintained. Yeah, we have talked about 4 different types of legacy systems to help us decide how to manage the legacy system. Yeah, don't forget that here both the business value and the quality of the application are important to decide the dealing with this legacy system. Okay, and these are the end of this chapter.